In 2006, a physicist at the Technical University of Dresden took a fragment of a 400-year-old Islamic sword and dropped it into a bath of hydrochloric acid. He was running a standard materials test, expecting to find common iron alloys. Instead, the electron microscope revealed something impossible. Hiding underneath the dissolved surface, the steel was packed with multi-walled carbon nanotubes and cementite nanowires. To put that in perspective, modern science didn't officially discover carbon nanotubes until 1991. Finding them inside a weapon forged in the 1600s defies the accepted timeline of human technological progress. These legendary weapons were known to the West as Damascus steel, but the microscopic secret hiding inside their blades didn't originate in the Middle East. It came from thousands of miles further east. Around 600 BCE, metal workers in the regions of modern-day Tamil Nadu and Karnataka began producing a highly specific type of crucible steel. The native languages called the melted metal uruku, a word the British would eventually anglicize into Wootz. By the time Alexander the Great reached the Indian subcontinent in 327 BCE, this steel had already achieved legendary status. Following the Battle of the Hydaspes, King Porus presented Alexander with a diplomatic gift of 100 talents, roughly 2,600 kilograms, of Indian steel. Ancient empires prized these heavy metal ingots more highly than gold. Arab merchants soon established massive maritime trade routes to buy these raw steel cakes directly from the South Indian coast. They shipped them across the Arabian Sea to manufacturing hubs in Syria. There, Syrian blacksmiths in the city of Damascus forged the imported Indian cakes into finished swords. When the Crusaders encountered these weapons centuries later, they noted a distinct, wavy, water-like banding pattern running entirely across the surface of the blades. For over 1,000 years, the most fearsome military technology on the planet relied entirely on a single supply chain, starting in rural South India. Which brings us back to that 2006 Nature study. How exactly did ancient blacksmiths engineer advanced nanotechnology? The process started with a strict recipe. Smiths packed specific black magnetite iron ore together with layers of bamboo charcoal and leaves from the avari plant. Then they sealed the clay crucible entirely to block out all outside oxygen. They buried these sealed crucibles inside charcoal furnaces, driving the heat up to 1,400 degrees Celsius for days at a time. Deep inside the crucible, an invisible chemical reaction took place. The molten iron absorbed high concentrations of carbon from the burning plant fibers. Those carbon atoms bonded together, forming microscopic, rigid, tubular structures trapped directly inside the cooling iron. Without access to electron microscopes or modern chemistry, Indian artisans utilized generations of empirical trial and error to master applied nanotechnology. If this metal was globally dominant and highly lucrative, production should have expanded. Instead, it completely vanished by the mid-18th century. The decline aligns with the expansion of the British East India Company and the fallout following the Indian Rebellion of 1857. In the aftermath of the rebellion, the British military launched a systematic suppression campaign. They confiscated and destroyed native weapons, while forcefully shutting down Indian metalworking centers. The final blow arrived with the British Forest Laws of 1862. These regulations prohibited Indian communities from accessing the specific timber they needed to produce their specialized charcoal. British colonial policies severed the generational chain of knowledge, effectively starving the technology to death. The sudden disappearance of the steel sparked a 200-year obsession among European scientists. Dozens of metallurgists desperately tried to replicate the metal in their own labs, but the results never matched the originals. Even Michael Faraday, the physicist who pioneered electromagnetism, spent years attempting to reverse engineer wood steel in 1819. He couldn't do it. In 2001, metallurgist John Verhoeven and master bladesmith Alfred Pendray successfully reproduced the alloy after decades of forensic analysis. They identified a variable hiding in the ancient supply chain. Indian smiths mined a specific iron ore vein containing trace impurities of vanadium. During the forging process, this vanadium acts as a chemical catalyst, forcing the carbon to align into that distinct wavy banding pattern. When that specific vanadium-rich ore vein ran out and the forest laws prevented the correct charcoal from entering the furnace, the delicate chemical balance broke down. Modern materials science didn't invent these advanced alloys. It took 4 centuries and an understanding of quantum chemistry to finally catch up to the empirical genius of ancient Indian artisans.